So now we will jump into things. It's funny you mentioned the international relations degree. That was a lot of fun to do. And believe it or not, I have another career doing computational social science these days, but I won't be talking about that work. Different vein of research, but something that is quite active in my lab. So I did actually get to use that degree later on in my career. All right, so back to biometrics. So the first thing I want to start this talk out with is the notion that biometrics isn't the only field studying faces. There is a very broad field out there in the world of science called vision science that is very interested in visual perception. And this field consists of psychologists, of neuroscientists, of cognitive scientists, and even a few computer scientists. And all of these folks are really interested in basically how the brain works, right? Very fundamental question, but one with increasing relationship to artificial intelligence and, of course, human biometrics when we think about the need for technologies like face recognition for not just security and defense applications, but human-computer interaction, mobile robotics, right? A whole bunch of different fields are interested in that within computer science. So it'd be good, I think, to take some broader perspectives and see what we can learn from other fields studying facial perception. Okay, so let me start out then with the following scenario. And again, this shouldn't be too far afield for the folks in this workshop. Let's imagine that there's a proprietary face recognition system that purportedly solves biometric identification with human-like ability. A claim, of course, we've all heard, right? Referring to latest algorithms in the research literature, referring to new commercial products that are out there. Human-like ability is often claimed based on some performance numbers that have been determined through experimentation. By all accounts, the software achieves superior performance on established computer vision benchmarks. And those benchmarks, of course, are these days large data sets, data sets of faces that have been collected from the web, usually social media, can scale upwards into the millions of images. And the idea is that when we've evaluated our system on such a massive data set, we have some assurance that it works in practice when we start to submit new faces to the system. So question here then is, how would we go about falsifying this claim of human-like ability? We're all good scientists, right? We're skeptical. We really want to kick the tires on this new face recognition system and verify that this claim is correct. And of course, right, the first thing we would turn to is the benchmark data sets. Maybe we would start by evaluating the system on different data sets, right, to see if it generalizes. We know cross data set effects are important, but that seems not really that satisfying when we think about what the system will have to do in practice, right? When new people are going to show up and try to interact with the system, submitting their face in the wild to the system. And so we really need to scrutinize this claim of human-like ability, right? What is going on there? Do we really have something that is perceiving faces like a human being would perceive those faces? And the dilemma then reduces to this thought experiment proposed by John Searle, the philosopher, back in the early 1980s. And this, of course, is the famous Chinese room scenario. So what's going on here and what's its relationship to face recognition? Or AI in general. So the way this thought experiment is traditionally articulated is as follows. So there is a box and there is a man inside this box. This man does not have any familiarity with the Chinese language, but the people outside of the box do. And so the way this system works, there are two Chinese speakers representing input and output. They send messages in Chinese into the box. And get messages also in Chinese sent outside of the box. They know there is a man in that box, and from their perspective, they believe that this man knows Chinese because input comes in, it's processed, and valid output goes out all in the Chinese language. So from their perspective, everything seems to be working, and this man must know the language because they can get valid outputs out of the system. Now, what is really going on inside of this box, the man has access to a codex. So he takes the input, which is in Chinese, looks up the symbol or set of symbols in the codex, finds the appropriate response, right? He's got a big bucket of different outputs, and then he sends the output out. And he's really leaning on this codex to get the process right. So he has no idea what these messages are, but he's always able to sort of go from input to output without any trouble. And that, of course, if we think about data structures, is a simple lookup table. Now, when we think about face recognition and other AI applications in 2022, we know that we're most likely leaning on a machine learning-based system that has been trained with data, a tremendous amount of data. And we're probably using an artificial neural network. And if we start to think about this, a question surfaces: how much of what is being learned by that artificial neural network is simply the lookup table, right? Memorizing the data set. If the data set's really large, that probably helps us generalize in the real world to many different tasks. And so that's okay, right? It's working. But that's not quite the representation we would want to learn for different problems, especially face recognition. So the takeaway here is we have to be aware of this situation, right? If we are memorizing as opposed to learning generalizable patterns, we could be in for some trouble when we use the system in practice. So this is what we want to figure out, right? When we have this claim of human-like performance, is that what we're really seeing, or is it really just a man in the box with a lookup table? All right, so this takes us now to a different style of evaluation, something that is very commonly used in the fields of neuroscience and especially psychology when it comes to perception studies, and that is visual psychophysics. So what is visual psychophysics? It's the probing of psychological and perceptual thresholds through the controlled manipulation of stimuli. Okay, what does that mean? What is a perceptual threshold? That defined in vision science is simply the threshold at which we can recognize something, right? If we are not exceeding, right, that threshold, that means we can't really figure out what we're looking at, right? There's some point at which the object, is too distorted, too uninterpretable to human observation, that we can't figure out what it is, right? But if we're above that threshold and it's quite clear to our visual system and we recognize it, then we can figure out what it is. And this is true of many different object categories, many different recognition settings, et cetera. So the idea with psychophysics is try to figure out where that is for a particular model system, right? That could be, an animal model system if we're neuroscientists, or it could be people if we're thinking about psychology. And for our purposes as computer scientists, that could also be an algorithm. So as we proceed with these experiments, we're interested in the careful management of stimulus construction. Ordering and presentation will allow for the precise determination of these perceptual thresholds. So this is going to be quite different from our data set analysis in that we're intentionally altering the stimuli in a very controlled manner. We're doing this in an incremental way to figure out at what point does the system break. So here's some examples from psychology studies involving facial perception. You can see here in this left-hand example, the study was meant to assess visual coherence with respect to faces and how that impacts recognition. So if you start scrambling the parts of the face, at what point does the person fail to recognize that this is a face? Something similar is going on here with this strange light bulb looking cartoon. Same idea, we have parts of a face in the cartoon and we're scrambling them. In which configurations does a person recognize that this, should be a face versus this is simply abstract art, right? I don't recognize whatever this is as a coherent object that I've seen before. And again, we do this incrementally. We look at different configurations to figure out what is going on. Okay, so this is not new. This is not, brand new stuff for science in general. This goes way back to early studies, early canonical studies in vision science. For instance, this very famous one from the 1940s, the minimum threshold for the stimulation of an individual photoreceptor. That turned out to be 1 photon of light. Right, so scientists were incrementally reducing the amount of light and doing this in such a fine-grained manner that they can control the stimulus down to that single photon and then still see cell responses in the retina, which is quite amazing. But it highlights how much control you have as an experimenter in this paradigm, right? I can basically do anything to the stimulus, right? I can sculpt light if I want to, all the way down to 1 photon, or I can do what I just showed you, right? I can create these graphics, right, and use those as the stimulus. So all of that's going to be pretty important as we craft these experiments. Okay, so let's link this back then to computer vision. So as I mentioned, when we think about evaluation in biometrics or visual recognition in general, these days, we're talking about large data sets. And this works in some capacity, right? We have useful computer vision systems, right? Like face recognition really does work. In fact, of course, we all know that was one of the early wins in computer vision in terms of getting a system to work well in real applications. And of course, right, we've got several decades of NIST evaluations, right, that are all data set based, right, that have been used to vet these systems, which are used in practice. So here's, the way it goes typically, right? Imagine we have two algorithms for object recognition in this case, right, A and B. We compute some summary statistic, right, over the data set. Could be top 1 accuracy, top 5, classification accuracy, whatever. And then we compare those summary statistics, right? So it looks, by the numbers here, algorithm B is better than algorithm A because those summary statistics are higher. Therefore, if I'm building a real system for, say, recognizing objects for visual search, I, of course, would use algorithm B over A because it's better, right? I did this experiment. I have a really good data set, ImageNet in this case, and I believe these results to be accurate. But what happens if we change the regime we're using for evaluation? Let's use visual psychophysics instead of just the straight up data set testing. What happens? So first, what I need to do is figure out what conditions I want to test, right? So I'm going to start out with these clean images, and I'm going to perform some sort of transformation on them. And I can turn to the world of image processing, where I have lots of different options that would map to things I would see in the real world. Same thing, computer graphics. I can do all sorts of interesting things to objects using the techniques of computer graphics, and I have a lot of power there because I control the entire environment. Maybe I can do some interesting things that, again, map onto real world situations that I'd want to be aware of. And if the system is failing, things I may want to use to explain why the system is failing, right? Which is, of course, the topic of conversation at this workshop. So imagine in terms of image transformations, I'm applying Gaussian blur, right, to simulate motion blur. Perhaps I'm adding different types of occlusion, right? Something we see in the real world all the time, something that people are good at negotiating, but algorithms tend to have trouble with. And of course, rotation, something, especially if I'm using deep learning, I want my network to be invariant to, because that's one of the promised properties, right, of representation learning. Okay, so now let's look at the difference in results. So number one, we're not looking at summary statistics in this regime. We're looking at these plots, which are called item response curves. And what we're doing here is looking at accuracy, just as we would compute accuracy over a data set on the y-axis. But on the x-axis, we have our controlled stimuli levels, right? So we're looking at, if we're considering Gaussian blur, increasing blur levels, right? Adjusting the sigma parameter of the transformation function we're using to add the blur to the images. So when we do this, we can then compare in curves, model A and model B. So remember, when we just did the data set evaluation, B was better than A in top 1 and top 5 classification accuracy. We can see here, when we look at Gaussian blur, all of a sudden A is quite a bit better than B, especially at high degrees of blur, right? It's far more reliable as an algorithm. B is outright failing by the time we get to the maximum sigma that we've tried for blur. Same thing, linear occlusion. A is a superior algorithm to B, right? It's surprising because in the clean data set, this wasn't an issue. But when it comes to rotation, model A is not as good as model B, right? So we see some advantage to model B there. So the takeaway here is that each of these algorithms has an advantage over the other in certain settings, and that was not apparent from the data set evaluation using the summary statistics, right? So this is going to be far more powerful because it's going to let us drill down into these individual conditions, which we're going to test. Okay, so let's talk about the limits of deep learning when we start into it with respect to these different image transformations and start looking at the problem from the perspective of visual psychophysics. So this is work that was led by my former graduate student, Brandon Richard Webster, who has since graduated and works at Kitware now. And my longtime collaborator and friend and startup co-founder, Sam Anthony. And I'll talk a little bit about our startup at the very end of this talk, because it's related to all this as well. Sam is a card-carrying psychologist. He did his PhD working on visual psychophysics for computer science applications. And so we've been developing these ideas for about 10 years now. So they're getting to be a bit more mature, which is good. So in this work, we're trying to figure out, could we define a rigorous evaluation regime for computer vision in general, right, for object recognition, using these techniques, right, of visual psychophysics, and then do some interesting experiments to look at real algorithms to see what's going on. So here is the basic process, right? And it's sort of what I just mentioned, though there are a few additional steps we need to be aware of. So first, we don't throw away data sets, right? We need data sets to start out with. And so that could be something like, right out of the box ImageNet, or it could be a data set that we render, right, using procedural graphics. And again, I think that's an underappreciated thing for many applications in computer vision, though of growing importance in areas like autonomous vehicles. But it's really, really nice for this application because, again, we have full control over what the stimulus looks like. And that allows us then to move on to our perturbations, right, what we're trying to change here. But before we do that, we need to figure out what images are going to be the best ones for experimentation. We know just from the regular data set evaluation that there are error rates associated, right, with the data sets and the algorithms. And some of the images, right, are not great because the algorithm out of the box is failing on them, but we don't necessarily know why. So what we want to do is really start with the images that work, perfectly or, as best as possible across an algorithm or a set of algorithms. So what we do in our process is to try to find what we call a preferred view. And this comes from the idea of a canonical view in cognitive science. You, as a person, actually prefer certain configurations of objects in terms of how they're posed to be able to recognize them. And this makes sense, right? Because it's probably going to be difficult for you, at least, on the onset, to recognize, say, a chair from the bottom, right? If I'm under the chair looking at it, that's not a typical configuration of this object for me, right, in terms of how I view scenes. So looking for, more standard posed images, things, again, we would be familiar with is what we're trying to do algorithmically here. And all we do is basically go through the data set and look for, the high scoring images, right? We pull those out, then we start to transform those images using our chosen transformation functions. And here, the world is our oyster, right? We can do anything out of the realm of image processing, right, or computer graphics. As long as, again, we have some controlled way to perform these operations so that we can map them to the x-axis, right, of our item response curves. And then that's what we're going to look at, right? That's the output of the system. So images, find the preferred view, transform those images, and then create our item response curves. So how do we then do the experiments? Well, there's more than one way to do it, which is really great. There are entire textbooks on visual psychophysics which teach laboratory experimenters how to do these things. So what we've done here is adapt some of these classical models to the algorithm scenario. Typically, again, these experiments are done with a person sitting in a laboratory. They're shown a stimulus, and then they have to make some decision, and then different psychophysical measurements are taken, right? For our purposes, we're usually interested in accuracy or reaction time for people. So the most familiar experiment, again, you may have seen this before, especially if you've done a psychology study, maybe helping a friend in a psych lab, or if you've dug into, again, some of the other human-oriented arenas in vision, the two alternative force choice task. So here, there's a sample stimulus shown. This is the thing we're going to match to. So we can see here, it's this airplane. This is going to flash up on the screen. It's going to disappear. And then we're going to present two alternatives, right? The matching alternate stimulus, which is another instance of a plane, right? So that would be the correct answer. And then the non-matching alternate stimulus, which is this friendly CG dog. And that, of course, is the incorrect answer. So if I were a person doing this task, right, I would then select the plane because this is obviously like quite easy. When we're doing computer-based evaluation, right, this is just one-to-one matching, right, which is something we're very familiar with, especially in biometrics. So plane should match to plane with the highest score. Dog should not match to plane. And so again, very, very basic task. And again, so we run this process over a number of different stimuli for a data set. But of course, the x-axis, every instance is going to have the same level of whatever transformation we've applied. So here it's Gaussian blur. You can see different sigma levels. And I'm not showing you all the levels here. These are real results for object recognition. But just to get a sense of where we are in the x-axis, you can see the levels of blur. right? That last one on the left is pretty challenging. The first one is unperturbed, so it's pretty clear this is a tiger. And then we're going to look at a number of different visual recognition networks, all very standard off-the-shelf networks that have been used for years. AlexNet, CafeNet, GoogleNet, and 2 different VGG networks, right, of differing depths. And then the red point here is human performance. So on the same task. So we can see there's a range of different performances across the different algorithms here, which of course we'd expect, right? Now, these are all trained on ImageNet. So it's not a difference in data. It's really a difference in the architectures. And that's particularly salient when we compare the 2 VGG networks. 16 and 19 trained with the exact same data. They're not terribly different in architectural design, right? It's just the depth is different. But we can see that VGG 19 is better at tolerating more blur. In fact, it's the best when we get to the end here. But we can see, though, for the one particular level of blur, the sigma value of 12, people are still better, much better than all these algorithms. And interestingly, GoogleNet is just basically failing, right? And that's a network that at least a few years ago was considered to be quite good. So again, this is something we would never get out of, ImageNet out of the box, but something that we learned quite a bit about with respect to blur coming out of this experimentation. All right, there's our human point. So what's nice here too, again, you can compare people to algorithms in a natural way because it's the same exact experiment. Other conditions, again, we're told that representation learning makes these representations invariant to transformations like rotation, right? Can we falsify that claim? Yes, we can. Here we can see all of these networks are really good at handling the rotation. And of course, people are good too, right? And so in this case, we can say, right, that performance of CafeNet and GoogleNet for this human point is basically at the human level of performance. Now, again, that's not generalizing to every possible image transformation, but that's something that is verifiable, which is good. Okay, but you may be thinking, well, that's only one way to perform an experiment. And of course, if we're thinking visual object recognition, there are a lot of different object classes, right? So what do we do about the 1 to n scenario? And of course, something that's very important for identification, right? The surveillance mode of face recognition. Well, we can do that too. So this is what we call MAFC. So again, we have our probe image, same exact probe image I showed you before. It's this airplane, but now we've got a full-on classification model, right? Which may have dozens or hundreds or thousands of different classes, right? All these different categories. And we're gonna match then, right, this image into this model and then get, right, scores for all of these different object categories. And right, if we get the correct one, it should have the highest score, all is well. And we can do the same process then for psychophysics and still get our item response curves in this mode, right? Because we're still looking for the correct answer. It's just we have more possibilities. It's not 2 alternatives, right? It's m alternatives, however large my classification model is with respect to the number of classes. So here we started to learn some really interesting things about these networks, some surprising things with important implications for, say, autonomous vehicles. So a curious contrast deficit, especially when it comes to things like driving, people have trouble seeing in the dark, right? And this is a low contrast problem, right? You can't resolve edges as you lose light, right? The objects start to blur together. And again, some people have, like night blindness, and this is very much a problem beyond the average person. But even an average person at a certain point, right? The room is too dark, I can't navigate it, that sort of thing. This shouldn't be terribly surprising to anybody. It turns out that algorithms don't tend to suffer from this problem. So we have, again, the human point in red here. So this is a really, really low contrast image, right? It's pretty washed out. You can see here, right, this most extreme stimulus maps to, on the left, right, at the leftmost plot, the red point here in terms of what the typical image would be. These are average curves, by the way, over many different categories. But you can see, right, the people are struggling, right? Accuracy is pretty low. Algorithms are much, much better. In fact, the VGGs, right, are basically perfect, right? They're not failing at all. Like, they're doing a great job. And that's not terribly surprising, right? If you've ever played with, filters in Photoshop, right, increasing the contrast of a low contrast image, you can get those, right, edges to pop back out, and then it's easy for you as a human to figure out what was in that image. So the information's there, right? It's just your visual system can't see it. These networks, though, aren't suffering in the same manner. That said, we notice the opposite, which is really strange. High contrast, which people typically aren't bothered by. Here, the algorithms are worse than people, right? So it's the opposite effect. The good news is you typically don't see that in the wild, right? That's more of I'm changing the display settings on my monitor versus I'm outside in the environment and I'm experiencing this effect. So really important finding, especially for autonomous systems. But as you'll see in a few minutes, it's also important for face recognition too. Okay, so that's the general idea, right? So we're changing the way we evaluate these algorithms. And again, we're not throwing away the data sets. The data sets are still useful. And of course, right, we've learned a lot using data sets. This is really a supplement, right, that lets us drill down into the individual conditions that may be causing failures, right? Maybe contributing to the error rates that we see in our data sets. After we did that piece of work, we were thinking, okay, we're really interested in biometrics. Do we need to do something different for face recognition, right? And the answer is yes. And it turns out Sam and I had always been thinking about this. We started out working on psychophysics for biometrics, specifically face detection. We knew there was some nuance when it comes to facial perception in both people and algorithms. There are some differences that we needed to account for in our process. And so we started to rework things and we came up with a new paradigm just for face recognition. So again, this is work done with Sam and also Brandon and a former student from my lab, Ali Kwan, who now works at my startup company with Sam, Perceptive Autonoma in Boston. Okay, so what do we have to change here to get this to work for face recognition? Well, there are a couple things that are pretty important here. Number one, when we do data set evaluation, we're typically looking at things like ROC curves, right? When we're assessing algorithms for, say, like face verification. So it's a little bit different than the straight up summary statistics we typically deal with. That said, this is basically a way to summarize data and still needs to be changed, right? Because this is not telling us why the system is failing. It's just giving us an indication of the true positive rate, false positive rate trade-off, right? That's what this curve represents. Again, useful, highly useful for things like face recognition, but not really telling us why the system is failing under certain conditions, right? Or what conditions are problematic. So how do we adjust the process for face recognition, specifically when we're looking for something akin to our preferred view? Because remember, that was the process. Start out with my clean data set, just like I did with object recognition. But now I need to find the images that are going to work really, really well out of the box because I want to start perturbing them. So I guarantee that what I'm doing to change the image is what's impacting the system's performance. So for this, we turn back to some old biometric theory on Doddington Zoo. So in the simplified version, I realize this has evolved over the years, and now there's like 20 or 30 different animals. But we're going to stick to the basic 4 here for this work. We know that some people have a lot of trouble using a system for whatever reason, right? The false negative rates are usually typically high for these people. And we call these people goats. That may be, for something like fingerprint recognition is a well-studied one, right? It's like people who are like manual laborers have like worn down their fingerprints, and so they're really problematic to get good quality data. The same thing happens in face recognition, though it's not that extreme. Some people, right, just have trouble using the system for whatever reason. That could be, algorithmically derived. That could be like a data set underrepresentation issue, right? There's a number of things that go into this. So those users are problematic. We need to be aware of that, right, in terms of our data set, in terms of the faces, right, that have high rejection rates, because we don't want to use those faces for this style of experimentation. Then we have our lambs and wolves. These are categories that are related to the false accept rate problem, right? So lambs are people that are easily impersonated by others. Wolves are people that are easily able to impersonate other people. And so since the error rate is a factor there, right, that's not ideal to pull those face images and use those as our data set. So what we really want are the sheep, right, the well-behaved users. They don't have a remarkably high false rejection rate associated with their images, and they're not being falsely accepted, right, as other users, or other users aren't typically confused with them. And so these are the ideal candidates. So we created an algorithm to basically mine the data set looking for sheep. We pull those out, and that's what we start with then when we do our perturbations. Then that perturbation process is exactly the same as the one I talked about for object recognition. We have these clean images. We pick transformation. Again, that could be something like Gaussian blur, and then we build our item response curve. And now, right, we've got a different set of curves that we can use to figure out which algorithm, is the best in a face recognition context. And ideally, then this will help us improve, say, our acquisition circumstances, right? If this is perhaps, facility access or some security application, to avoid these problems from cropping up, right? Because we want low error rates across the board. So what did we learn when we did this? We learned quite a bit. We looked at a bunch of different transformations. We looked at a bunch of different algorithms. We can see here in terms of the algorithms chosen, we have more variety than the ones we chose for object recognition. VGG face, right? Again, a representative convnet that's been used for years, right? Deep learning based for face recognition. We looked at two different implementations of Google's FaceNet, OpenFace, and a GitHub repo simply called FaceNet, which claimed to be a reimplementation of the paper, the work in the paper. Google never released that open source, which was unfortunate. Shame on them. And then we looked at two other sort of unconventional approaches by today's standards. This algorithm labeled SLM simple is also a convolutional neural network, but it was not trained using backpropagation. It was randomly screened. So the weights were simply randomly instantiated, and then it was just evaluated on the data set to see its performance, and done many, many times, right? And the best one was chosen. We thought this might be interesting. Again, it's weird, right? Like, why would you do that? Well, it short circuits training, but it also gives you something that's not overfit, right? Because it never was trained to any data set in a proper way in terms of tuning the weights. It was really just checked against a validation set. And then we also looked at OpenBR, which of course is an older toolkit for face recognition that contains handcrafted features. We kind of wanted to, again, to see, is the machine learning with, artificial neural network perhaps not as good in some settings, right, as some older stuff, right? That's something I think we forget about. We have a lot of algorithms, right, that have been developed over the years. And again, because overfitting is such a persistent problem, it might be interesting, just throwing it out there, to look at some older stuff too. So right away, we discovered some really interesting things we would not have found, I think, otherwise. So as I mentioned, OpenFace and FaceNet are supposed to be re-implementations of the same exact algorithm, right? The same paper was used as a reference point. You can see here the green and the magenta curves are wildly different, right? There's huge gaps between them on every single plot I'm showing you here. And we've got lots of different transformations in this work. We've got, just on the slide, occlusion. We've got facial expression, again, using computer graphics to change the face. And then some color transformation here. You can see this wide gap. Why did that happen? We had no good explanation for it just based on the plots, right? Because again, it was supposed to be the same exact thing. So we went back to the repositories and started to look at the code and the notes associated with the code. And what we found out, digging into the source code, that FaceNet was not a faithful reproduction of Google's FaceNet. The programmer took some liberties, made some changes to the algorithm, changed the data it was used to train with, and it turns out that this is pretty much a degenerate algorithm. This doesn't work well, even though if you look at the benchmark numbers reported on the data set, right, it looks very close to what Google got in their paper, right? And so I think this programmer was misled because I don't think they moved past that data set, right? They just tried it, saw that it was, in the ballpark, and declared victory. And of course, right, no one should ever use this implementation. You can see here from these results, right, it's very, very bad. Other interesting results too, that SLM simple network, the one that wasn't trained with backpropagation, was really, really good in terms of being invariant to some of these transformations we did in the computer graphics space, right? Changing the expression of these faces, right? It was much, much more tolerant to this. Why is that the case? Well, these particular expressions were underrepresented in the data sets, right, that were used to train the machine learning models, which is interesting. And then finally, OpenBR, right? Did that have any advantage over more modern algorithms? As it turns out, it did, right? It's not the worst algorithm here, which of course, everybody would probably assume, right? Because again, it's a more modern era of machine learning. We've moved away from the handcrafted features like LBP and HOG and all these other things. But a system making use of those things is actually better in some cases than the more modern convolutional neural networks. And again, it all depends on the setting. Other transformations here, and also looking at the human versus machine performance. Again, we started off this talk with this question, how could you falsify this claim, right? This system is at human level, right? We should trust it like we would trust a person. For some of these conditions, right, and some of these algorithms, the algorithms are indeed better, right? Pink noise or 1/f noise, right? It looks like people are more impacted than a number of these algorithms. Again, we see the same contrast effect I talked about with object recognition, right? I would trust almost all these algorithms, just not the bad Google FaceNet implementation from the bad GitHub repo. Everything else is better than people, right? As we can see for most of these transformation points. Again, humans had a lot of trouble, interestingly enough, with some of these expressions. I think part of that had to do with the subtlety, or at least the perceived nature of these facial changes. Because we were using these CG heads, but the algorithms were better. So all this is pretty interesting in terms of understanding, right, the landscape of performance difference. Okay, so I'm gonna close out the talk here by discussing another application of psychophysics that's related to faces, and then I'll take some questions. So here's a really fun psychophysics-driven task. We found through the course of our work that it's not just about evaluation. We can actually take these measurements from people and use them and fuse that data into algorithms and do some really, really interesting things. So Sam and I, when we started this work, we actually were able to make algorithm performance better, and we're continuing to do that. In fact, there's some very, very recent work from my lab, which just appeared in TPAMI, on infusing these psychophysical measurements, especially reaction time, into algorithms for handwritten document transcription. So the algorithm like more closely reads like people, right, in terms of trying to interpret handwritten characters. But here's something that's completely different and something that's fun and also related to faces. So this is CNNs for subjective face attributes. Again, work with my friend Sam and another former student, Mel McCurry, who's now working at a biomedical imaging startup in the Boston area. So subjective attribute predictions, what is that? So most of us, again, because this is a biometrics audience, we're familiar with, the objective facial attributes, right? Things like, gray hair, blonde hair, brown hair, wearing glasses, not wearing glasses, small nose, big nose, etc. Right? Even emotions, right? It's like I can kind of gauge like smiling, frowning, map that onto some continuum of emotion, right? All of that's pretty standard in the world of biometrics and effective computing. But what about these other things, right? That are important for social psychology and especially first impressions. Trustworthiness, dominance, IQ, and even perceived age. That's the one I think that most biometrics people are familiar with, right? There are a number of different machine learning challenges in terms of, like guess this person's age, where we don't have the ground truth, but we're trying to infer what this person's age might be. And as people, we do this all the time. So what's interesting about all of these different attributes, we're not saying that we have ground truth for them. What we're saying is how closely does the algorithm match a crowd as the crowd makes assessments about these first impressions on these faces. So, what does that mean in practice? Well, I don't know what the ground truth value is for the trustworthiness of Julian Assange or Edward Snowden. I could probably make some guesses about their trustworthiness, but I don't actually have that. But again, I can sort of, based on looking at the face, make a guess, right? And then everybody in the world could do that, right? I could assemble a big crowd of raters and get everybody's, opinion on these different attributes. And that gives me some data to work with. And then what I want to do is build a model, right, that'll sort of gauge these things, right, in a manner that the crowd would. And that's neat for all sorts of applications. Imagine I wanted to train an actor, right? Could I get, Benedict Cumberbatch to better act like Julian Assange, right? I want to try to match, right, his performance with the look of Julian Assange and have people rate that, right, to figure out if he's doing a good job or not, right? That's something, you can think of a bunch of different applications. We were mostly interested in this work and in the social psychology implications, right? Like what does it mean to make a first impression? How reliable and how repeatable is that? What does that say about people? And I'll emphasize this has nothing to do, again, with the trustworthiness, dominance, intelligence of any of these people. Again, in some sense, those things are unknowable. We're really just trying to match the crowd ratings. So how does this relate to psychophysics? Well, we perform a different type of psychophysics experiment, but with people here. We present people with the stimulus and we ask a question involving a Likert scale. So here, click one of the buttons below to rate this face from 1 to 7, where 1 is the least dominant and 7 is the most. Right? And the person selects, a value for that, and I collect this rate over a number of different images, and I have a number of different raters rating each individual image, so I can calculate some variance around each particular attribute. This alone is quite diagnostic and quite interesting when we think about social psychology experiments. Again, looking at these 4 attributes in particular, people are really decent at assessing age, I'd say. So, here, is a set of different faces, representative, in terms of the degree to which, right, the face exhibits, right, age over time, right, or increasing IQ, increasing dominance, increasing trustworthiness. You can see, of course, the babies are the minimum. This elderly person, right, is the maximum for age. That makes sense. So the human experiment, in some sense, is working just based on that. IQ is really fascinating. Again, we didn't control for the babies. So the babies perceived to be the least intelligent. I guess that's true to some sense. In some sense. And then familiar face recognition was a confound here. I'd say Gandhi, for instance, was rated to be the most smart out of everybody in terms of the data set. Dominance, again, babies, the least dominant. I guess, again, not surprising. Middle, or yeah, sort of like, I guess like men in their like 30s and 40s were considered to be the most dominant. Women less dominant overall. And then trustworthiness. We have this really bizarre looking person putting some sort of rubber over their face as the least trustworthy person. Elderly grandmother types, they were rated to be the most trustworthy in terms of people. So again, we can get an individual distribution for all of these different attributes. They do vary depending on what the attribute is. And this is going to become then part of the training data we use to create an algorithm that's going to be able to predict these different attributes. And so again, as I mentioned, these do vary. Important, each individual image was shown to a number of different raters, right? You can see here, we try to get over a dozen raters in some cases. We've got over 24 different raters. So that smooths out some of the noise, right? You shouldn't trust just one person when you do these experiments. You want to do this over many different people, right, for one image to make sure that outliers aren't strongly impacting the process. Because again, we're going to need this information when we build a regression model that's going to be able to predict these same things. Dataset patterns, again, some interesting things we observed just collecting the human data. If you're wearing glasses, you're perceived to be smarter, right? Not terribly surprising. Age, if you're wearing glasses, you're perceived to be older, right? Perhaps a little bit more distinguished. Age given female, right? So there are some gender effects here. Women were rated to be younger in appearance compared to men. And trustworthiness given occlusion. If there was some occlusion present on the face, those people were rated to be less trustworthy than those without occlusion, right? So what is this saying, right? I think you're learning about some biases in human perception overall, and also the way people perceive things in the environment, right? Again, occlusion is something that's very, very common. We have evolved over time to negotiate circumstances like evolution, or like occlusion. And so this is really, really interesting to pull out, right? And to try to model. So as I mentioned, we're interested in regression here. So we built a number of different regression models using different types of recognition systems. Again, starting off with some really basic handcrafted features. That's kind of the strawman model. It doesn't perform that well. We're looking in terms of performance, an R-squared statistic, looking for correlation, right, with the crowd ratings. So how close does the algorithm make predictions with the human ratings? And we looked at a bunch of different convolutional neural networks. Eventually, we settled on the best configuration, which was a multi-objective attribute network from Terry Bolt's lab at the University of Colorado. And then we optimized that with some hyperparameter optimization. And we got pretty decent correlations. R-squareds upwards of like 0.4 for some of these attributes. Age was really good. It was over 0.6, depending on how much we trained the system. eventually getting up to over 0.7 as we continue training. This is sort of a tricky thing, right? I think to many computer vision people, they're looking for like really, really high scores. In the world of social psychology, an R squared over 0.4 is phenomenally good. Like that's an excellent model. Even very, very weak correlations, very low R squareds are considered to be quite significant in terms of findings, something over 0.1, for instance. So here, we're definitely learning some interesting patterns in this data. We still tinkered with the architectures a bit and the training regime a bit to see if we could eke out some better correlation. Basic thing, right? What if we started with a pre-trained network trained with, VGG face or ImageNet as opposed to random weights? Does that make things better? And it turned out this did improve performance a little bit. But what's really interesting, when we looked at the visualizations of where in the images these networks were looking to make their determinations, the pre-training was focusing on completely different areas of the image compared to the random weights. When we looked at the random weights, we found regions of the face that, again, not terribly surprising from a psychology perspective, that we would expect to be important, right? Specifically the eyes, right, and the mouth region. But when we switched to the pre-training, the backgrounds tended to be more significant. Now you may be thinking, aha, like, this is some weird data set bias thing and none of this really worked the way you expected, but that's not true for first impressions, right? Context matters, right? And again, you're not really thinking about this in many cases when you're sort of judging other people, but the lighting is a pretty important factor. Think about Hollywood movies, right? And dramatic lighting. Right? Lighting is an art, right, in Hollywood for a good reason, right? It affects how we perceive the face. And so we see those effects quite heavily when we did this transfer learning exercise and didn't use random weights. Those networks were really focusing on, again, the context of the image as opposed to the face itself. But we still, again, got good correlations out of both these things. And again, you can look at different styles of interpretation, right? Saliency from occlusion, right? Again, this is a workshop on explainability. So most folks, I'm guessing, know like there's more than one way to do it to assess where these models are looking. And again, the parts of the face that were not terribly surprising, the eyes, the brow region, and the mouth again. And the coolest thing about this is you can run it in real time, right? So here's a video of Edward Snowden. You can see when he's not making good eye contact, when he's looking down, his trustworthiness rating is pretty low. But as he becomes more animated here in a second, you'll see the score starts to go up, right? Now all of a sudden he's looking a bit more natural, right? He's engaging with his interviewer, and I sort of trust him more, right? He seems like, a good guy, right? At least that's what the model is thinking. And maybe that's what I'm thinking too when I look at him, not knowing the circumstances of his background, of course. Okay, so to wrap up here, what other attributes are interesting? Well, at Perceptive Automata, the company I co-founded with Sam Anthony, that's up in the Boston area, we're interested in autonomous driving, and we're really interested in pedestrian behavior. So wouldn't it be interesting if we could make predictions about pedestrian awareness and intent, especially when they're not in motion, right? A big headache for autonomous vehicles and getting them to work well is people standing still at crosswalks. You as a human driver can easily infer what they're going to do in the future, and you don't even think about it, right? You blow through the intersection when you know they're not going to cross, right? Because perhaps they're distracted, right? Perhaps they don't look like they intend to cross, right? You're gauging their body language, their affect, etc. We're trying to build models that operate similar to what I just showed you with respect to these subjective personality judgments, but for specific attributes that are useful for human driving. So again, another type of biometric, another type of body analysis. All right, I will stop there, and I'm happy to take any questions in the last few minutes here from the audience.